Hi everyone, my name is Ben Oler. I'd like to welcome you to today's webinar from Asylum Research, an Oxford Instruments company. Our topic today is Piezoresponse Force Microscopy. Today will be an introduction. If you want to learn more, be sure to sign up for the Advanced PFM webinar on Wednesday of this week. We're honored to have Dr. Sergey Kalinin joining us as co-presenter today, along with Dr. Roger Pruksch. Dr. Kalinin is the director at the Institute for Functional Imaging of Materials and theme leader at the Center for Nanophase Material Sciences at Oak Ridge National Laboratory. Dr. Kalinin has published more than 400 scientific papers, is a co-inventor on more than 10 patents, and has received numerous awards and honors for his research. His research interests are focused on the scanning probe microscopy of electromechanical, ferroelectric, and electrochemical phenomenon, and the development of big data, deep data, and smart data approaches in imaging for design of new energy and information technology materials. Dr. Pruksch is president and co-founder at Asylum Research. He's been active in AFM development and research for more than 20 years and has been particularly active in the field of PFM and nanomechanics. Please feel free to ask questions during the webinar. You'll see a text box in the webinar interface where you can enter these. We'll collect the questions, and Sergey and Roger will address as many of them as they can, as time allows, at the end of the presentation. If we're not able to answer all of them, we'll be sure to get back to you individually. Today's webinar is just one of several planned for the year. If you don't want to miss these, please go to our website, www.asylumresearch.com/webinars, and you can email us to subscribe to the mailings. Also note that the presentation today will be recorded and available for viewing later. Simply follow the same link you were sent in the registration confirmation email. So let's go ahead and get started. Roger will be speaking first.
Thanks for the introduction, Ben. I should say before we start that I got involved with this general field of PFM, Piezoresponse Force Microscopy, almost a decade ago. It's been a really great experience. There's a lot of smart people that work in this field, really interesting instrumentation challenges, and really great physics and material science. Today, I should note that a lot of the material you're going to see today already appears in an application note that you can download from our website that's at this address right below here. So the way it'll play out today is that Sergey Kalinin will give us an introduction to piezoelectricity. He'll talk specifically about measuring piezoelectricity with scanning probe microscopy, AFM, PFM. One of the challenges with PFM is sensitivity. So one of the ways to improve your sensitivity is just to turn up the voltage, turn up the volume. So we'll look at higher voltages. We'll also talk about using the contact resonance of the cantilever to amplify the tiny PFM signals that we'd like to measure. And in specifically with that, you can do that at a single frequency. There's some problems with that, and so we'll talk about multi-frequency techniques that are able to reap the benefits of that amplification while not suffering from a lot of the downsides of using a single frequency technique. Specifically, I'll talk about dual AC resonance tracking, a technique called DART, and Sergey will talk about band excitation. One of the smart people I've had the pleasure to work with for this last decade is Sergey Kalinin, and he's going to start off this webinar with an introduction to piezoelectricity. Sergey?
Thank you very much for the introduction, Roger. It's a great pleasure to have an opportunity to talk about the PFM here. And let me start with the history of the PFM. So whatever type of science you are doing, it's always curious to trace the origin of the science to some specific moment in history. And in case of PFM, it is actually remarkably history. You can arguably say that PFM and electromechanics were actually the beginning of modern science. So it all starts with the experiment of Luigi Galvani, who applied the electrical bias to the frog leg and observed how the frog leg twitches. That was basically the discovery of electricity. We still use the words as galvanize, which is something we hope this seminar will make all of you. We use the words galvanometer, galvanoplastics, and so on. So it was a discovery of electricity, but it was also the discovery of the electromechanical coupling in the biological systems. So we can say that in the beginning of modern science, there was actually electromechanics. And of course, frog leg is a very complicated system. The simplest form of the electromechanical coupling is the piezoelectric effect. And in this case, we can sort of separate two effects. We can have the direct piezoelectric effect. If we have a crystal and we apply force, we will generate the charge on the crystal surfaces. And this is how the electric lighter, for example, works. And we can define the inverse piezoelectric effect. So in this case, we have the same crystal. We apply the electric bias, and if we apply bias in one direction, that crystal expands. If we apply bias in the different direction, the crystal contracts. And the coupling coefficient, the D33, is basically the same between the charge and force and strain and bias. So you can prove from thermodynamics that it has to be identical. The question you may ask is whether this piezo effect exists only in the level of crystals and frog legs, or does it manifest in smaller objects? So in other words, how low can we go? And the answer is it's actually the fundamental part of nature. For example, if we consider a simple polar molecule, so we have two atoms which have opposite charges, which are separated by the chemical bond, which have some given spring constant. If we put this molecule in the electric field, it will create a force acting between these two atoms. And then we can evaluate the change in the bond geometry based on the charges. And it turns out that estimate for a single chemical bond is about 10 picometers per volt, which compares very favorably to the piezoelectric coefficient, for example, of quartz. So in other words, this electromechanical coupling is ubiquitous in systems with polar bonds, if not forbidden by symmetry. So if positive and negative molecules compensate each other, then naturally the overall response is zero. And secondly, even if the bulk response is zero, then surfaces, interfaces, and low-dimensional systems with the broken symmetry are likely to have the unusual forms of electromechanical coupling. And this is what we are interested in. So, how universal is the electromechanical coupling in materials around us? The answer is it's extraordinarily universal. So there are multiple applications for basic piezoelectric and ferroelectric materials. So these include ultrasonic imaging in medicine and national defense, for example, sonars. There are multiple emergent applications such as non-volatile ferroelectric memories, energy harvesting, actuators, sensors, microelectromechanical systems. So these are all applications of piezo and ferroelectrics. Another broad range of systems with this very strong electromechanical coupling are the ionic and electrochemical systems. And those include batteries and fuel cells. And those typically electromechanical coupling is a problem. You really don't want a battery to expand and contract too much because it tends to not work very well. But nonetheless, it's something that we need to know and understand. Another example would be the electroactive polymers that are used in artificial muscles or actuators. Third example would be the biological system. So when I talk, I convert the electrical signals of my nerves into the acoustic waves. When you hear me talking, your ears convert the acoustic waves back into the electric signals that neurons detect. It applies to such dream applications, the molecular electromechanical machines. So when you see the movies of the robots flowing in the blood and curing the cancer, they need to move. And likely this motion would be electromechanical in nature. So this is a very, very large spectrum of existing and future and only dreamed about materials and applications. So, however, before we make these applications a reality in whether 20 or 50 years, we really need to be able to study the electromechanical coupling locally. Let me illustrate why. For example, if I want to study a piezoelectric effect in the quartz single crystal, this is relatively easy. I can take a single crystal, I can put 2 electrodes across it, I can apply 100 volts, and I can measure how the crystal expands by several nanometers. I can take the same crystal, go to the X-ray, or if you are in Oak Ridge, to the neutron scattering machine, and I can study in detail the structure of this material. I can study the phonons, sort of everything that defines the physics of this system. And then I can say that the properties measured of the macroscopic object can be directly linked to the structure measured on the level of the single unit cell, because all unit cells are the same. Unfortunately, this approach doesn't work for more complicated systems, for example, aforementioned biological system. So, for example, I can purely theoretically apply 2 electrodes to the mouse and apply voltage across it, and most likely the response of the mouse would be extremely strong. It will have a memory effect that would be nonlinear, and probably mouse will get extremely unhappy. However, I can no longer go to the synchrotron and study its internal structure using the scattering techniques. If I want to understand electromechanical coupling in biological systems, I have to do it on the level of the tissues, I have to do it on the level of the single cell. Ultimately, I have to do it on the level of a molecule. Turns out that the same is true for inorganic materials. For example, single crystals tend to be an exception. If we want to study grains and domains, if we want to study the nanoscale phase-separated structure in relaxers, we really need the local probes to study the electromechanical coupling, ideally on the length scale of cells, phase-separated regions, or molecules. How can we do that? So in macroscopic systems, we measure the response to the uniform external field. We apply the electrodes, we apply bias, and then we measure strain generated in response to this electric bias. The question is, how significant can be these responses? Turns out that they are not that large. We can measure nanometers, we can measure fraction of the nanometers. Even for macroscopic systems, the piezoelectric responses are small. In nanoscale system, situation is much worse, because basically what we want to do is to measure the displacements of order of picometers. If we measure the inverse piezo effect, or currents of order of femtoamps or smaller, if we want to measure the direct one, over the length scale of 1 to 10 nanometers. This is really, really complicated. So it turns out that, luckily, we can actually do that. And this is the technique of the Piezoresponse Force Microscopy. So what we do here is we have an AFM, so we have a cantilever and the sharp tip on the end of this cantilever. We apply electric bias at the end of the tip, and because of the specificity of the electrostatic of the system, the bias will be concentrated in the very small volume of material below the tip. If the material is piezoelectric, this will create expansion and contraction of the material, and if we measure this cantilever deflection, we basically get the information about the local piezoelectric responses. A very remarkable aspect of piezoresponse microscopy is that the response depends only on the bias we apply to the system, but not on the length scale of the problem. So in other words, if we apply bias of 5 volts over 10 nanometers or over 1 meter, we measure exactly the same response. That's a little bit of magic, but that's how the Piezoresponse Force Microscopy works. So how can we expand this principle? We will use the properties of the SPM. For example, we can measure the vertical surface displacement, what we call vertical PFM, via the flexural oscillations of the cantilever, but we can also measure the lateral displacement of the surface by the torsional oscillations of the cantilever. And you can see that how the photodiode of the modern AFM allows to distinguish vertical and the in-plane components. We can also get insight in the orientation of the polarization inside the material. For example, if the polarization goes upward, the material will expand for one voltage polarity, and if it goes downward, it will contract. The way we can distinguish it is based on the phase of the response. We can look at the several examples of the PFM images. So these are examples of the very simple, very trivial single frequency piezo-response measurements on the lead zirconite titanate ceramics. So this is a kind of prototypical material for PFM. What you see on the first step set of images, the yellow ones, is basically surface topography. And this is just how the surface looks like. And polishing of the polycrystalline ceramics typically produce the pattern of grains polished at different rates. So you see several grains on this image. At the same time, if we detect the piezoelectric signal amplitude and phase, we see ferroelectric domains inside those grains. And you can see that there are domains within all three grains, but the domain patterns are different because the grains have different crystallographic orientation. So the amplitude image gives us the strength of electromechanical coupling, whereas the phase image gives us whether it is polarization generally oriented upward or downward. Notice that we can get both vertical and lateral signal, and this data is complementary. So there is clear correspondence between the vertical and lateral images, but the information is different. So you see the domain walls in both of those images, but the signal at which domain manifests is totally different. In fact, we can proceed with the more sophisticated analysis in this case. For example, we can take a lead titanate film on platinum. We can visualize the topography. We can visualize the vertical piezo-response signal. So here we plot what is called the mixed PFM signal, meaning that we multiply the amplitude by the cosine of phase. We can measure the lateral signal, and I mean, we all know that displacement is a vector. So if we measure vertical and lateral components, we can reconstruct two components of the response vector. And then we can plot the orientation and the magnitude of the vector using this vector map. So this color legend shows the direction in the XZ plane, and the saturation of the color shows the strength of the piezo response signal. And from this vector information, we can actually reconstruct the individual components. For example, we can map of the magnitude, and we can get the map of the angles of the response. And in this case, we can gain some insight into the structure of this material.
Thanks for that, Sergey. I'm going to talk a little bit about some of the experimental reality of making PFM measurements, and I put in this slide picometers with an exclamation mark because picometers are small. If you recall, Sergey showed you the amplitude that we measure is this piezo sensitivity multiplied by whatever voltage we apply to the tip. Typically these numbers are on the order of a picometer per volt, maybe up to 500 picometers per volt for something like PZT. And that means that the measured amplitude is very small, and that typically we'll have a low signal-to-noise ratio even for relatively high D33s. It's a small number. One of the things I like to show is the following. This little cartoon here shows if this is a carbon atom, which is roughly 2.5 angstroms across, a picometer is that little dot right there, which you might have thought was just an accident. It's a tiny, tiny number, and so it's actually it's actually quite remarkable to me that AFMs are capable of routinely measuring those kinds of distances. This example here shows a barium titanate thin film, and this is a particular material with a sensitivity, a piezo sensitivity that's about a couple picometers per volt. This was made below resonance at a volt peak-to-peak drive, and you can see here in both the amplitude And in the phase images, the signal to noise is very low. This is from Alexei Gruverman, and Alexei and his students drew a little domain in here. This is a common sort of technique to look at ferroelectric materials. So they reversed the polarization in this. So you could see a structure, but you can see that the signal to noise is very small in this. And in fact, if that D33 was much smaller, we might not be able to even see it at all. So how do we make a bigger signal? Well, one way we can turn up the signal is to simply turn up the voltage. In the limit that your sample responds according to that equation, if we want a bigger amplitude, we just make that tip voltage larger. And in many samples, that works very well. It also allows you, if you have the ability to apply large voltages, it may give you the ability to look at switching events in materials that maybe have switching at higher voltages. So you can turn up the voltage. If you do that, at some point, you may come to a point where the polarization is actually being continuously switched by that applied voltage, in which case your signal won't grow anymore, and in fact your domain structure may be destroyed or removed. If you keep going even beyond that, it can be even more dramatic, where you can reach dielectric breakdown and cause damage to both your tip and your sample. This is a photograph. That's the stub of a cantilever that was melted away, burned away by an arc when this film, I think we applied about 100 volts to this thin film here, and reached dielectric breakdown and started to conduct, leaving behind nothing but wreckage and destroying the cantilever. So if we'd like to avoid that unpleasant situation, where the cantilever is destroyed or the sample is destroyed by too high a voltage, what can we do? Well, Mother Nature has been very nice with us in the PFM world, where she's given us a built-in amplifier, and that is the contact resonance of the cantilever. It amplifies a smaller signal by basically the quality factor of that resonance. So in PFM, and I can't remember if Sergey mentioned this or not, but already we're driving at a frequency where we're above the 1/f noise limit of most AFM systems. So the contact resonance is typically even at a much higher frequency. So with typical PFM cantilevers, it might be up somewhere between 200 and 400 kilohertz. At contact resonance, or in the case of contact resonance, if we're used to a low frequency measurement where the amplitude is given by the voltage applied to the tip times that piezo sensitivity, at resonance it gets amplified. So this expression is valid only identically at resonance, but it's an approximation near resonance. And basically the cantilever response is multiplied by whatever that Q factor is. And typical Q factors is, I think, I may have mentioned at some point, is 20 to 100, maybe 200, and so you get an improvement in your signal and noise of anywhere from 20 to that 200. This graph here just shows you a sort of typical contact resonance of, this is a silicon lever coated with metal on a PZT sample. I'll look at it a little bit more in the next slide. But there's the contact resonance right there. You can see, especially in the phase data, the noise away from resonance is actually very fairly high, and there's a lot of jaggedness in it, a lot of jumpiness in it. As we go through that resonance, the amplitude goes up and the signal to noise improves dramatically. Again, as we go above resonance and the amplitude goes down, that signal to noise starts going away again. So let's look at operation near resonance a little more closely. These curves here show idealized, these are calculated curves where we have the amplitude and then the phase. Now I've divided the phase up into two separate curves. This is one for, let's call it an up domain, and if the polarization reverses, we get a 180-degree phase shift, so that whole curve gets put up by 180 degrees. That's the theoretical behavior. Now this is actually the data I showed, or some of the data I showed in the previous slide, but the way we generated this is I used that trick that Alexei used earlier in the barium titanate. I wrote a domain here, so I have, let's call it an up domain and a down domain here, color-coded on that sample. These tunes were made at those two different locations. So this was made over the up, and this was made over the down. And as I mentioned in the previous slide, you can see the relatively poor signal to noise away from resonance. It improves as we go through resonance, and then it gets bad again. As we go over the up and down domain, you also see that the phase shift, let's look at this phase shift, if we call that 0, this phase shift over here over the down domain is 180 degrees different from the other domain, as it is above resonance as well. Okay, to explore this a little bit more completely, we made a little movie here where we have a theoretical response of a PFM cantilever over a sample. This sample has down domains, up domains, down domains, and so on that have different spacing. We've also built into this model some surface roughness. Now the surface roughness changes the contact area between the tip and the sample in such a way that that changes the stiffness of that contact. And then, of course, when you change the stiffness, that makes the resonant frequency move up and down. The ideal phase in a perfect situation is plotted down here. So over the down domain we get 0, over the up 180, and so on. And the amplitude's plotted down here. We'd also expect the amplitude to be equal across all those domains. Let's just play this movie here real quick, and you can see what's happening. You see the green tip moving along. Now bring your eyes up to this part here. This is showing what's happening to the contact resonance as we move around. This bar here is where we're driving it. So we're driving it below resonance. And you can see what's happening here is the phase is playing along. It's actually doing a pretty good job of reproducing the ideal phase structure there. We're getting good fidelity between the two. However, we do have a lot of noise in there because the signal noise, because we're below resonance, it's a noisy signal, even though it is reproducing the sample data very well. So we got good reproduction of the polarization of our sample, but I didn't like the signal to noise. So what I'm going to do now is I'm going to say, well, let's use that amplifier. Let's use the contact resonance. And so instead of driving it at below here, I'm going to drive it as close to that resonant frequency as I can get, because my signal to noise should improve there. Let's see what happens when we play now, when we scan that sample. So there's your tip going. And as you can see, there's a lot less jaggedness in the phase response. It looks pretty smooth. What the heck is happening there?
I don't know if there's no longer organizers
like
as a panelist, you should be able to.
Now, what's going on? Well, if
you can already speak, right? So it's all
back and forth in response, changing contact stiffness of this tip, hands over the surface, we get crosstalk between that change in the stiffness and the phase output of the sample. If we just zoom in on that graph, you can see that the fidelity is very low. We're not getting good reproduction of that ideal phase, even though our signal to noise is very good. So what about an experiment? What's the reality? It is actually that bad, and sometimes even worse. In fact, things that can make it worse is that tip can actually change during scanning. So contamination, wear, fracture, and so on can actually change the contact resonance and cause even larger problems. This is an example of that. So this was a PZT sample again, and these are just a couple pictures I took. I've been carrying these around for years, so I don't remember too much about taking them, but you can see roughness in the sample up here. You see roughness in that signal. There still seems to be some clear differentiation of things, but there's a little streak here where something happened. This image shows an even worse sort of situation. There's a sudden chip change. The contrast changes. One of the phases is very noisy, and you can actually see the structure here, which if you look at the topography, you would see was linked directly to the topography of the surface. This is another example, maybe not quite so bad, but another PZT. There's a single crystal here in the topography, and you can see these streaks and other things in the phase image, and then even more stuff in the amplitude signal that correlates with that. As another example in that, I'm going to go back to that thin film barium titanate sample that I showed you in the beginning. This was the low frequency PFM, so far away from resonance, and you can remember that signal to noise was rather poor. At the same time, at least we get something like 180-degree phase shift and the amplitudes in the noise. But if you look at this was actually made near resonance. The signal to noise is much higher. Like you can see structure in the amplitude here. But because the contact resonance is also playing games with this thing, it's not a very clear differentiation of the different domain types. They don't match. There's streaks. There's other artifacts coming through. So actually interpreting this data, as it turns out, becomes difficult. I will show you in a little bit here the idea, what we can do with tracking the resonant frequency to improve on that. So keep this slide in mind. I don't think I showed this before either. Just you note up here, this is the actual sample topography measured with the AFM. So you can see it's a very flat sample. That scale there is about a nanometer peak to peak. So it's a very flat barium titanate sample. So we still would like to use that great gift of the cantilever resonance. I showed you in the previous slide how even a really smooth sample with basically as close to zero topography as we can get still has some crosstalk between that changing contact resonance and the measured amplitude and phase. So one answer to this is to try to track the resonance. So try to make the cantilever always stay at its resonant frequency instead of just driving it at a fixed frequency. And how do you do this? Most electrical engineers would suggest you use something called a phase-locked loop. Phase-locked loops are fairly simple. The idea is very simple, at least, and that is that if you look at, say, this red curve here, which is the phase of an oscillator, simple harmonic oscillator going through its resonance. At resonance, it's at 90 degrees. And there's the amplitude. You're at the peak value of the amplitude. Now imagine that resonant frequency shifts, and so say in the case of this blue curve, the frequency drops. That means that the phase here will actually go up to this little point here. And so if we have a feedback loop that looks at that phase and locks it into 90 degrees by changing the drive frequency, it's going to automatically change this frequency from F to F prime, or F naught to F naught prime, lowering the resonant frequency and keeping it on resonance. Unfortunately, if you think about it for a second, this doesn't work for PFM. Because in PFM, the drive phase is actually the parameter that tells us about the polarization direction of the ferroelectric material, and that's changing all the time. So if you're scanning along, and maybe let's pretend that the contact resonance hasn't actually changed at all in this case, but the polarization does. So if the polarization changes but the contact resonance doesn't, then you're still going to get a phase shift that goes into this. And so if we start off again with this red curve, now as that polarization gives you a phase shift, it's going to move that 90-degree point off to the side here, and the end result will be that the changing PFM phase actually ends up driving you off the cantilever resonance. So we need to find a different solution to this other than the phase lock loop to try to keep on resonance. So what do we do about that? And this is a nice segue into the final topics of this webinar, and that is multi-frequency techniques to take advantage of resonance while at the same time not suffer with so many of the disadvantages with respect to crosstalk. So there's two papers I reference here that we published in 2007, one on this technique, dual AC resonance tracking, the other on band excitation. I'm going to talk about DART, dual AC resonance tracking, right now, and then Sergey will give you a nice introduction to band excitation. And really the philosophy of both is that two or more frequencies are better than one. They enable us to get beyond the limitations of those single frequency measurements and take advantage of the contact resonance. So DART, dual AC resonance tracking, the idea is as follows. What we do is we take, just like with conventional PFM. We're exciting the cantilever voltage potential with a voltage that is a sum of sinusoid at one frequency and the sum of the sinusoid at another frequency. Conventional, I should say, sorry, conventional PFM just has one frequency there. If you actually look at, you drive that voltage with this and then you measure that response, the deflection signal actually looks like this in the case of DART, because these two frequencies in the case of DART are really close together. They're close together, and the difference is that beat frequency in this response. We can take that beat frequency, analyze it with two separate lock-ins, and we get an amplitude at one frequency, a phase at one frequency, and then an amplitude at a second frequency and a phase at that second frequency. So this can be used, the amplitudes in particular can be used as a replacement for that phase lock loop. Now recall, with the phase lock loop we use the phase to see how that frequency is moving. That doesn't work because in the case of PFM, phase is actually an observable that gives us information about the sample. In fact, it's not controlled. It depends on the polarization of that sample. So by going to an amplitude measurement, we avoid that. So the idea is very simple. If we have F1, F2 being a frequency, and our original contact resonance is this solid black line here. Now we chose those F1 and F2 drive frequencies such that A1 and A2, the observable amplitudes, are the same. So the difference between those two amplitudes is 0. They should be identical in that point, or close enough to it. Now let's imagine that we go over a sharp feature in the sample such that the resonant frequency goes to a lower value. And so that's this dashed curve here in the amplitude. And what you see there is that the amplitude at the lower frequency, F1, actually goes up because that peak shifts to the left. The amplitude here in blue of the higher frequency actually drops. And so this is what this kind of behavior is what we use in this feedback loop. Now instead of phase or amplitude, if we look at the difference between A1 and A2, and we use that in our feedback loop to track the resonant frequency, we can get a measurement that is independent of the drive phase. So by putting that in there, we have a phase-independent feedback signal, and that lets us follow the resonance, so we get all the benefits of that built-in amplifier from Mother Nature, the cantilever, contact resonance, without, or at least with greatly reduced crosstalk between the sample topography and the amplitude and phase. So I'm just going to show you one example of that. There's a lot now out in the literature, but this was one of the first ones we looked at. And you're familiar with these first two images. This is the low frequency, so way below resonance. I don't remember where it was, maybe 50 kilohertz, something like that. And you can see the signal to noise is poor. This is conventional single frequency PFM, close to the contact resonance. You can see a lot of crosstalk between the sample topography and the data. And then these simultaneous, well, sequentially made at the same location using DART. This is the amplitude, and this is the phase here. The phase shows a very nice 180-degree phase shift, very high signal noise, very crisp domain delineation in this. And the amplitude signal, the amplitudes on the inside and outside are approximately similar. There's a beautiful 0 at the domain boundaries for both the inner and outer domains, and the signal noise is quite nice in this case. So I really like this example showing it. Okay, that finishes up the DART portion of this last bit of the webinar. I'm going to turn you over to Sergey Kalinin now, who will discuss band excitation. Thanks.
So the DART method that Roger have illustrated is one way to perform piezoresponse measurements on the topographically non-uniform surfaces. An alternative, or if you will, complementary approach to DART is the use of what we call the band excitation method. So let me illustrate what it is and how it is implemented and what it does, starting from the basic physics of the tip surface junction. So when we have a cantilever interacting with the surface, in a good approximation we can represent it as the oscillator. So the simplest form of the oscillator, which is called simple harmonic oscillator, is defined by three parameters. So if we plot the amplitude versus frequency, we need to know the resonant frequency, sort of the position of the height of the position of the center of the peak. We need to know the amplitude, the height of the peak, and we need to know the quality factor, which is the measure of the energy dissipation in the system. So its meaning becomes obvious once we go from frequency domain to the time domain. If the system has strong damping, then the induced oscillations decay very fast. If the system has weak damping, then oscillation persists for a longer amount of time. But in any case, the system requires at least three parameters to describe it. At the same time, the lock-in based methods measure only amplitude and phase, and the phase loop based methods measure only resonant frequency and the strength of the response, which basically means that classical single frequency methods are undefined physically. They measure only two parameters, where the system is. So the classical single frequency methods are undefined physically. They measure only two parameters, whereas the system is defined by three. So how can we understand that? So look at the classical sinusoidal excitation. So we generate the excitation signal, for simplicity by function generator. We send it to our cantilever. We detect the response. Using the lock-in amplifier, we generate the amplitude and phase at a single frequency. If we look at the signal in the Fourier domain, we can see that both excitation and the detection signal are basically just a single delta function in the Fourier space, just one line. And if our view of the world is so narrow, it's no surprise that we don't see the full amplitude frequency response. So the idea of the band excitation method is actually to go away from this single frequency excitation method, and rather than excite system by a single sinusoidal wave, to excite it by the band of frequencies. So what we do is we generate a band of frequencies in the Fourier space. We use the inverse Fourier transform to generate the signal in the time domain. So we no longer excite system by sine wave, we excite it by this much more complex signal. Instead of the function generator, we now have the arbitrary waveform generator, and instead of the normal detector, we have to use the data acquisition card. We detect a signal which is also not sinusoidal anymore. It's a little bit more complicated. We do the Fourier transform, and if we have the signal now, it is a response in the band of frequencies, so we can narrow this band around the resonance. In fact, this approach allows us a very significant flexibility in the choice of how we want to excite our system. So these are several examples. For example, we can control the phase in order to control our excitation signal. If we use one form of the phase distribution, we have what we call a sync signal, which looks like this. So it is very localized in time, but carries a relatively little energy. If we start to tweak our excitation phase, we can make the distribution of the signal in the time domain more uniform, and in the limit we will have basically a chirp signal. So we can kind of tune our excitation to serve our purposes. Do we want to have a cleaner response, or do we want to have a more intensity response? So what we learn with the band excitation? The answer is very simple. If we excite the system by the single sine wave, we learn the response only at one frequency. If we excite the system using the band excitation, we learn the response in the band of frequencies, which means that we basically recover this full amplitude frequency curve, or rather the segment of the curve that we're interested in the given frequency interval. And we can fit it using the simple harmonic oscillation model and simply recover the amplitude, resonant frequency, and the quality factor at each point in the image. And these are the few examples of how the band excitation works. So for example, we scan across the sample surface, and now we have the full amplitude frequency and phase frequency curve at each position on the sample surface. We can represent this data in the form of this two-dimensional spectrogram. So classically, you will have a trace line across the surface. In this case, we have the two-dimensional trace line. And you can already see what kind of information we learned here. So imagine that we were scanning the surface as just one frequency. We would have a very strong variation of the response, which has nothing to do whatsoever with electromechanical activity. It would be simply due to the variation in the local resonant frequency. As it is now, we can use the mathematical fit in order to see how the resonant frequency changes across the surface, so the lossy of this response curves. And this tells us where are the resonances, and this is the mechanical properties. We can also see the strengths of the electromechanical coupling, and these are, for example, ferroelectric domains. So now we completely separate the amplitude of the electromechanical coupling and topography. In fact, we can also extend this approach for more complex methods. So we'll talk about it in more detail on the next seminar. But we can take the band excitation method and combine it with the spectroscopic modes of the PFM. So in this case, the prototypical mode is the Piezoresponse Spectroscopy. So imagine that we apply a waveform like this, sort of this modulated triangular wave. So if we apply a small bias to the sample, then nothing much happens. If we apply a larger bias, then we start to nucleate a ferroelectric domain below the tip. And if we concurrently measure electromechanical response, it basically changes because the part under the tip contracts, the part outside of the tip expands, so they partially compensate each other. If we apply even larger response, the domain grows. So at some point, the response from domain under the tip and surrounding matrix will exactly compensate each other, so we have a coercive bias. If we keep increasing bias, then domain will grow much larger than the detection volume, so our response saturates. If we go in the opposite direction, then typically if we go in the same polarity, nothing much happens. If we go to the opposite polarity, we, for most materials, start to nucleate the domain of the opposite polarity below the tip, almost like a Russian doll. And if we repeat the process, we collect the hysteresis loop of the material. So it turns out that this is a very powerful method to probe polarization switching in ferroelectrics, but it's also subject to local crosstalk. And what we can do is basically combine this piezoresponse spectroscopy and band excitation method. So we substitute the sinusoidal wave by the band excitation waveform, and we get this four-dimensional signal which can be deconvoluted to give us the piezoresponse loop, the resonant frequency loop, and the dissipation. It turns out that amplitude of the resonance tells us the information most relevant to the polarization switching, and the evolution of the resonant frequency and dissipation gives us valuable insight into the mechanical change in the system, in the ferroelastic switching, in the behavior of ferroelectric relaxers or morphotropic systems. So the materials which are really interesting because of their giant electromechanical responses and the broad applicabilities in sonars or energy harvesting. So we'll talk about it in more detail in the follow-on seminar. And this is the example of how the raw data in this case looks like. So this is a typical spectrogram showing the evolution of the signal as a function of time when the voltage is swept along the triangular waveform. You can nicely see the changes in the resonant frequency and changes in the signal strength. And this is how the results look like if we extract the evolution of the amplitude and the hysteresis of the resonant frequency and Q factor. The next question you can ask is, what does it mean? That's where the real science of the PFM starts. So in some cases we can use the numerical models, for example those developed by Malotsky and Anna Mrazovska. In more complex cases we need to consider the phase field modeling, for example developed by a Longqin Chen group at Penn State. But this is where the really interesting science starts, and we'll talk about it in more detail in the next seminar.
Thank you, Sergey. That wraps up the technical presentation part of this webinar. There are a few other details I want to give you before we call it a day. If you're interested in what you might want to do next, the first thing to think about is don't miss our Advanced Topics PFM webinar later this week. I think it starts on Wednesday. That is something Sergey mentioned before and Ben in the beginning. I have to put in a plug for the Center for Nanophase Materials Sciences at Oak Ridge National Laboratory. If you're interested in coming there and using some of these advanced techniques and working with really awesome scientists, send Sergey a note to that email below. And finally, if you are looking for more information, there's a lot of resources out there. There's a lot of conference proceedings from the PFM workshops that have gone on over the last few years, as well as a number of books you can have a look at. Finally, I mentioned this in the beginning, but many of the materials, a lot of the materials you saw in this presentation are available in the form of an application note that you can get at that website below. With that, I'm going to wrap up the presentation and turn it over to our MC, Ben Oler, who will field any questions that you may have at this point. Thank you very much.
Okay, thanks a lot, Roger, and thank you, Sergey. We did get a number of questions during the webinar. If you haven't submitted your question yet, there's still time to do so. Just go ahead and type those into the web interface. The first question will go to you, Sergey, and that is, what range of materials can be measured with PFM?
Well, it very much depends on range in which parameter space one considers. So basically, as long as the material is solid and forms a sort of semi-reasonable surface, meaning that it doesn't react with atmosphere and is more or less stable, pretty much anything. So all the way from materials with Young's modulus of about something like 10 megapascal all the way up. So from very soft materials, gels, whatever, squishy biological systems, all the way to solids.
Okay, and then Roger, as a bit of a follow-up, can you comment on the sample preparation requirements that are typically required, including, do you need a conductive substrate, special tips, special probe holder?
Yeah, so you do need some conductive. You need a conductive cantilever of some sort, and you need to make an electrical contact to that conductive cantilever. You should have the substrate grounded or at a potential. In the case of some of the high voltage measurements, that does put some special constraints on it. And the other thing to be careful about there with high voltage, of course, is safety. You should be avoid putting body parts onto high voltage. You'll see a very strong electromechanical reaction in yourself. I think that's it. I guess so. The other part of it is that sample cleanliness is actually very important. And so the surface that you're scanning, this is a nanomechanical measurement, and so your tip sample contact can play a very strong role in the response. We see this all the time with ferroelectric materials. They tend to have charged surfaces, which tend to collect stuff, contaminants and other things from the surface, and so sometimes you have to actually sort of scan away at them for a while to scrape off that stuff to get to the actual ferroelectric surface.
Okay, thanks, Roger. Sergey, I'll give this next question to you. What information can you get for non-ferroelectric, but rather pyro or piezoelectric materials?
For materials which are purely piezoelectric, we can basically observe things like piezoelectric domains, which in this case would be simply regions with a dissimilar crystallographic orientation. And in some cases we can study surface terminations. For example, there was a set of work done by Alexei and Brian Rodriguez when they observed materials like gallium nitride, which are piezoelectric, and in this case, if the surface is gallium terminated, has one polarity, if it is nitrogen terminated, has another polarity. So it's possible to study surface terminations and crystallographic orientations.
Thanks, Sergey. One more question for you. Can you comment on background noise in PFM measurements, and especially how to identify it and how to avoid it?
Well, there are many sorts of the noise possible, right? So I'm sure that Roger would be able to add to it quite a lot, but our background noise is the basic thermal noise in the system. So this is a sort of typically white noise in its origin. There is not much we can do about it other than go to very low temperature measurements. Second type of noise is the 1 over F noise, which appears in electronics and in some sense limits how much information we can get in PFM if we simply increase the image accumulation times. So this one is also something that we cannot do much about, and it's just there. The only way to deal with it is go to the better electronics. Then we start to deal with the environmental, acoustic, and electromagnetic noises, sort of most notably 60 Hertz cycle, which appears between due to the crosstalk between the electric power sources, microscope electronics. So this one is very easy to identify simply based on the periodic waves in the image. So how to select and identify them? In some cases it helps to record the signal at each pixel as a function of time and try the multivariate statistical methods that can separate noise components. But I'm afraid there is no universal answer.
This is Roger. I'm gonna stick one other comment in there, Sergey, and that is that in your microscope there is a chance for electrical crosstalk. So as you're driving, say, your tip at a high voltage, that can result in currents that can excite resonance in other mechanical parts of the microscope. For example, if you have a shake piezo for doing tapping mode or something else like that, you can actually shake that piezo that has nothing to do with your sample, but that can lead to a signal that can appear as a background, which can cause confusion on imaging sometimes.
Okay, thanks. Roger, another question for you. How can I get access to Band Excitation without traveling to Sergey's lab at Oak Ridge?
Well, first of all, I'd recommend you do travel to his lab in Oak Ridge. I think it's a great place to visit. If you want to do Band Excitation, we will be announcing fairly soon here, or maybe we already have, a partnership with a company called Look Instruments, where we'll be providing another accessory module that will allow pretty advanced band excitation measurements on Asylum microscopes.
Thanks, Roger. Sergey, a question for you. What about PFM measurements in ultra-high vacuum? Do DART and band excitation work under those conditions too?
Yes.
Okay. One other question, again for you, Sergey. Why is the amplitude for both domains not exactly the same?
This is actually a very interesting question. So the correct answer, the answer is that we don't know in detail. There can be the responses both due to the microscope and due to the fundamental physics of the surfaces. So Roger can comment on the microscope-dependent responses in more detail because he actually have studied in detail using this beam scanning across the cantilever approach. With respect to the possible physical origin is that we have a different screening mechanism. So if you think about it, polarization can never exist in the unscreened form. So if we calculate how much free energy is associated with the free polarization charge, it's enough to basically shift the Curie temperature 10,000 degrees lower. So in other words, it's impossible. So in air, the polarization is screened by ions. So for positive polarization charge, it's typically hydroxyls. For negative polarization charge, it's typically protons. If we don't have access of water to the surface, it would be screened by whatever electrons and oxygen vacancies or whatever mobile ionic carriers are available. Now, when we consider the contact between the cantilever, between the tip and the surface, these ions will be kind of sticking inside this gap because they're chemically bonded to the surface. Since they have different physical sizes, the effective field acting on material would be different for positive and negatively oriented domains. So at the first glance, it sounds that difference in the chemical termination of the surface shouldn't really affect PFM, right? Because we talk about the difference in gap of order of tens of picometers, whereas our tip surface contact is about 5 nanometers. However, it matters because all the size effects in the gap are magnified by the ratio of dielectric constant between the gap and the surface, and ferroelectrics tend to have a very high dielectric constant. So in this case, even small gap can have a disproportionately large effect.
All right, thank you, Sergey. We are running a bit long. We'll go ahead and take a few more questions. If you have questions that you haven't asked yet, go ahead and do ask them. We'll have to get back to you individually here in the next day or two. Next question for Roger then. What would you recommend for a frequency difference between the two frequencies in dart mode?
So the two frequencies, when you drive the cantilever with the two frequencies, as I showed in that slide, that you get a beat frequency back, which is the difference between those two drive frequencies. And you would like that difference to be at a rate that's higher than the feedback bandwidth of the microscope. So in practice, depending on the microscope, you might have a feedback loop that's between 1 to 5 kilohertz, and so you'd like that difference to be above that. So usually, if I'm scanning slowly, it's at least a few kilohertz, and if I'm trying to scan more rapidly, maybe 10 to 20 kilohertz.
Okay, thanks. Another question for you, Sergey. How do electrical scanning modes work under aqueous conditions?
So it depends on the frequency. If we operate our driving frequencies around hundreds kilohertz or higher, they actually operate exactly the same way as an ambient environment. It's a little bit counterintuitive, but there are two reasons why it happens. So first of all, in aqueous environment, our cantilever dynamics is different than in air. However, it is different by hydrodynamic functions, so there is a whole set of work by John Sader about it. And it turns out that at the high frequencies, cantilever oscillation in air and liquid are very much comparable because the only effect is the hydrodynamic damping, which is kind of low in these conditions. The second consideration is the electrochemical reactions and whether the cantilever can deliver sufficient voltage to the surface. And it turns out that at high frequencies it is still the case because aqueous solutions have ionic conductivity, which means that at low frequencies of order of hertz and tens of hertz, we will have electrochemical reactions. In high frequencies, the ions are simply not fast enough to respond to the electrical bias applied to the probe. In fact, there is a recent very detailed paper by Liam Collins and Brian Rodriguez about the electrochemical force microscopy, which explicitly discusses this issue. But practically it goes to the point that we can scan, for example, PZT ceramics at 100 kilohertz in reasonably concentrated solution, say 10 millimolar, and using 100-volt peak-to-peak oscillations, and we get a normal PFM picture. If we start to lower the frequency, then somewhere around 10 kilohertz, we will start to see the very rapid onset of electrochemical reactions, meaning whatever you can come up with, the gold from cantilever dissolving and redepositing on the surface, bubble formation, and so on and so forth.
Okay, thanks, Sergey. I'm just going to give you one more question. I apologize if we haven't gotten to all of your questions. Again, we will get back to you individually. So Sergey, last question. How do you know the polarization direction when you're using band excitation?
Typically for ferroelectric material, we do a very simple check. If we have a ferroelectric material, we simply create domain of known polarity and use it as a reference point.
Well, thank you very much.
So if we apply a positive bias, we know what domain polarity we have.
Oh, so sorry, Sergey. Again, thank you to both of you. I'd also invite you and remind you that we have the Advanced Topics in PFM webinar this Wednesday. There's still plenty of time to register for that. If you go to our website, www.asylumresearch.com/webinars, you can register for that. I'd like to thank you for attending, and again, we'll get back to you with any outstanding questions.